still.
Got it. So.
Steve.
Okay, so now is the talk that everybody was waiting for and didn't know. We have Wael coming in and bringing us threat modeling and AI.
Hey everyone, thank you for hanging out until 4 p.m. and I really appreciate you being here listening to me. It's my first time being on stage, so bear with me if I stumble a little bit. So I'm Wael, and let's see what's on this. Oh, I can read it here too. All right, so the title here is Everyone's a Threat Modeler. I truly believe that. I think a lot of us alluded to it earlier today. And this is really for beginners. So anything I shared, please do think through it through that lens. This is not really for someone experienced. And a lot of the things I want to share are things that I believe would be useful learning tools. So I'm in security now. I started my career in network engineering. And I am curious about where this AI thing is going. But disclaimer, I'm a pro-human species, so I don't think, my goal is not to replace humans, and I will fight the bots till the last breath. So that's sort of where I'm coming at it from. Is anyone familiar with this framework? Yeah? Okay, so as I said, I started in network engineering, and I used to have a love-hate relationship with it. But it's an excellent learning tool. And when you start out as a network engineer, half the challenge is figuring out where the problem is, right? Usually the thing that comes is in, it's broken, can't communicate, or there's a performance degradation, and then off you go trying to resolve the issue. And once you know at what layer of this stack the problem is, then you can fairly easily get to the solution. And earlier this year, I gave a course in the foundations of security engineering. It's a defensive course, not into offensive security. And the reason is, just like when we teach civil engineering, we talk about material science. We don't go straight to demolition, and I think that's the thing in InfoSec, and I find that a little strange. Now, granted, there's a historical context, which is that. There was a lot of security by obscurity. And thanks to folks that did offensive security, they would really point out some issues that are kind of under the rug. But I do think we're at a point where security has to be inherent to how we build products and services. So this model, while not perfect, and sometimes you have overlap between protocols, but it really does give a unified basis for network engineers to communicate and design. And yes, vendors don't always adhere to it perfectly. But as I went on about the course to teach students foundational security engineering, I realized there was no equivalent to this. And I wanted to get to the topic of threat modeling, but before getting there, I wanted them to first, if they're faced with a new system, how do they understand it first before even thinking about how to secure it or look for threats? And I came up with something that I believe, so this works well for, excuse me. So yes, I wanted an equivalent that would work for general systems and not be network specific. And the framework, I call it CCCS, which stands for Control, Compute, Communication, and Storage. And so my theory is that most useful systems are designed in a predictive and repeatable way. And I'm going to give examples, see what you think or if you agree. So those are the 4 layers we talked about, and we're going to define them a little bit. So your control layer is the one that is responsible for managing and orchestrating everything around this system that is producing work. So it's not a layer that is doing the work, but it's everything else. So whether it's your logging, it's your identity and access management, right? So it's not producing the work, but it's managing the system for you. And pretty much every system has control elements that fit into that layer. The second one would be your compute layer, and that's the one that's doing the work. The compute entities are either physical servers or virtual machines or containers or lambdas. Anything would fit into that bucket. And this is why you pay for the service. It's because of those elements, not the control elements. On the communication side, so any useful system will need to receive data, transmit data within the system. Information is going to move around. Anything that is involved with communications would fall under that layer. And finally, storage, same thing. So you're gonna, once you act on the data or the information, you store it either temporarily or permanently, and anything to do with that we would categorize as a storage element. So how does this work in practice? So let's take the example of a processor, of a microprocessor. You have a control unit in the microprocessor, and along with the clock, the goal there is to manage the instruction flow and execution flow. On the compute side, you have the ALU, which is what is actually doing the bit manipulation or the calculations, in this case arithmetics. And then for your communications, whether it's communicating within components of the processor or shipping the results out, you have I/O interfaces and buses. And finally, for storage in the microprocessor world, it's usually registers. Of course, the goal here is not to delve into the specifics of hardware at the processor level, but just to show that, okay, you can kind of look at something like a processor and abstract those components into those buckets. Same thing, if we look at an operating system, by the way, I have a slide that has mistakes, so don't take pictures of that afterwards. The slides will be made available. So, because it's repetitive, and the goal here is not to read every line, but same thing. For an operating system, the kernel really does a lot of the management stuff. On the compute side, this is everything in user land, right? Those are your applications. That's what produces the useful work in the operating system. On the communication side, it's your network adapters, your stack, all of these things. And on the storage side, anything from a USB stick to your SSD, this all classifies as storage. So again, we can take something like an operating system and we are able to decompose it in such a way. Now, why are we doing this? I'm going to get to that, but the main goal is that once we decompose it, we can then methodically go through every layer and say, what are the types of threats that we think exist at such and such layer, right? And finally, for a modern cloud service, which I'm sure everyone has anyone used AWS or Google Cloud or Azure. Again, this has a mistake here. You can see the storage part refers to the registers and the processor. So obviously, in a cloud environment, storage means S3, block-based storage, object-based, all of those things would fit into that category. On the control side, how do you control your tenant as a cloud tenant? You log into your management console, right? Or you use the APIs to manage your tenancy as well. So all of that falls under control, as well as the logging controls that AWS gives you. On the compute side, anything from virtual machines to any of the other compute-based services would fall there. And for communication, anything to do with virtual networking. So we don't have any hardware components, but anything to do with whether it's virtual, your VPCs, your virtual routers, the security groups, all of that falls into controlling communication. So great, now we have a framework that provides a convenient starting point for the next step. So, which is, doing more in-depth analysis of that. And, one of the things that security engineers kind of constantly contend with, or are expected to contend with, is, hey, here's a new thing we're doing, let us know if it's okay, and now you need to sign off. And it's something you may have never seen before. Obviously it helps if you've used it or you've actually have a background in it, but oftentimes than not, you're not going to be familiar with it. So you need to basically get quite intimate with it to then be able to evaluate whether the way it's being done is, relatively secure or not. So this framework, what I like about it is because of this semi-rigid structure, it leads to predictable outcomes, or at least that's one of the goals. It's modular, so any changes in any of the layers can be independently sort of updated, right? And we expect there to always be changes, but you should be able to slot them in where they need to be. And it's scalable, I think I kind of demonstrated that you can apply it across different scales, so, which is flexible. You don't want something too inflexible where every, few months you need to abandon and move on. So, this is great as a learning tool. So if you sit down, do a whiteboard, or you take your time with it, it's great. You're gonna end up learning, you're gonna end up researching the system, but in the real world, how would you operationalize this over time? It's quite tedious to do so. And I decided to give AI a go with this. So rather than just tell an LLM to go and decompose a system for me, just like that, and it would do it, right? An LLM will never say no to anything, and that's probably one of the issues with it. I decided to constrain the way it would work by saying, hey, here's a nice framework I have, and I want you to decompose it based on this framework, and tell me what you see, or what you come up with. And so, is everyone familiar with Kubernetes? It's an orchestration framework for containers, so it will manage how you run your container environment, along obviously with many other things. And I decided to ask an LLM, specifically GPT-4 by OpenAI, to decompose Kubernetes based on triple CS. And so this is the actual architecture of Kubernetes. This is the official documentation. And look, if you're experienced, if you've never worked with Kubernetes, in fact, this is exactly what happened with me when I was first exposed to it. I looked at this and said, oh, okay, there's some control plane. Like the same reasoning is there, but if someone's fresh to the field, they don't quite know where to start, right? They're going to be looking at this. There's all these acronyms, and they're not quite sure what does what. And then subsequently, how do they prioritize what needs to be secured or not? Or how do they go on about doing that? So this is what, I'm just making sure I don't know if there's a mistake with this one as well. The font's too small for me to read, but first of all, this is actual GPT-4. I had planned a live demo, but I ran out of time because to get to the output in this format, there's some overhead to be done, and this is something I'm working on making available for anyone that later would like to experiment with. But so I'm sharing the actual output there, so I didn't really do anything apart from defining triple CS and asking it to decompose it accordingly. And it actually came up with the list of the components. And now Kubernetes is a well-known project, so it's going to go, it has the documentation for it. And so it listed the components that it thinks fit into the control layer, and then I took the time to say, okay, this is actually accurate, and those descriptions are right. So look at it from the standpoint of someone that knows nothing about Kubernetes, and now they say, okay, tell me what this is, and it's going to break it down into that. I think that's quite reasonable. That's a good starting point. Same thing for the compute layer. It breaks down the Kubernetes entities that carry out compute functions, and it tells you what each one does. On to communications, and then on to storage. And I'm going through them because it's immaterial to get into the details here. I just want to show you what it can do, so we can get to the next important part. So now that we have this thing broken down and decomposed in a way that we asked for, then I asked the LLM to conduct a threat model based on the outcomes of the previous stage, right? So first, I defined triple CS, then I told it to decompose Kubernetes based on triple CS, and then I say, hey, based on this decomposition, do a threat model. Now, there's one thing I didn't insert here, which is that I also define certain security primitives that I want to see for every layer of CCCS. So in the course that I teach about security from first principles, and I talk about what is the minimum, what are the minimum design level elements we need from a security standpoint for the control layer, for the compute layer, and I provide that also to GPT-4. And that's what I'm going to share with you now. So based on the decomposition, I asked it to conduct a threat model. Okay, I mentioned that. And so that's, again, actual GPT-4 output, and it's telling me about 2 threats that the API server faces. And if I were to ask GPT-4, just, hey, give me a list of threats, they're not going to be in this format. So I asked for things that I thought were important if I were to take this and show it to an engineer, right? And this is just based on experience when when I take things to engineering and say, hey, we have a problem, I'm trying to answer all the questions that they would typically ask. So first is, I want a description that someone can understand without too much effort, right? So for example, and excuse me, the font is too small for me to read here. Okay, anyway, we have a description, a textual description of a threat, which I'm sure, I don't know, I hope you can agree, but you can easily craft a JIRA ticket with this type of description. It's not very hard to understand. Then I also ask it to provide evidence of why I should care about this threat. So, as we mentioned earlier, LLMs hallucinate, and when I was playing around with this very early on, it would list threats, and then I look at this and I say, that's weird, this component doesn't even exist here. So I said, okay, I wanted to also give me some evidence for why this is a threat. So in this case, it does tell you, hey, the API server handles all requests, so it's talking about a DOS attack potentially against the API server, so great, yes, it exists, it's part of the stack. And then threat likelihood is always important, right? You can go to an engineer and say, oh, this is very serious, and then what's the likelihood? Well, based on the way things are deployed, it's not likely to occur, or very low likelihood, and so you do have to take that into context. Now, Stride and ASF, I don't use them, but of course a lot of people do. And I thought, hey, how well would this thing do? And it was actually very easy to say, I want you to give a Stride category, right? Maybe where you work, you do use Stride, you do use ASF, you may use yet another formal framework. Very easy for me to tell it, hey, give me those categories. And based on my cursory review, it looks like it does stick to them, so that works. And then a suggested priority, that's really crucial there. Also, I ask it to tell me why it thinks this is a high or medium or low. This is also important for discussions with engineering as you make certain decisions for trade-offs. And then countermeasures. Obviously, this is important. I don't want to just go with a problem. I want to try to provide some solutions. And if the LLM can help with that, or at least get me halfway, I'm interested in that information. And finally, a practical attack example. And why is that? I don't think we need to provide justification every time we're trying to highlight a security design flaw. However, a very common counter is, well, this is not a real thing, it'll never happen, right? And so again, if an LLM can assist with that rather than me go and do the research, or especially if I'm new to the field, I'm probably not going to have a lot of experience. I may have not seen a lot of evidence of attacks, so I may not be able to conjure up the attack scenario myself. I figured this would also be a useful tidbit there. So, if you recall for Kubernetes when we decomposed it, there's about, I think, 4 components in the control layer. And so now I'm just showing you what it listed as threats for each one of them. So this was the API server, now this is the etcd component, and then the controller manager, and then for the scheduler. Again, so same format. This is easy to kind of go through. And now moving on to the compute layer. Same thing, listing threats. Now, you may ask me, how is it that it's always exactly finding 2 threats for each? Yeah, good question. I don't know. This is something that you can go back and say, give me 4 threats. And then sometimes 3 of the 4 are accurate and then the 4th one is not. Again, this is early days. I'm just literally sharing what I'm kind of experimenting with here. And then this is for the containers. This is for the pods. And then for the, yeah, and it found threats for all of them. Now, you may also say here that, well, a lot of these could be inaccurate. And, you know, I totally agree. But I think it's a good thing for someone that's new to go and say, okay, is this really a threat? Because now they're really going to start digging deep into it. They're going to improve their learning, and they may stumble on something else in the process. And you know what? Who hasn't dealt with false positives with tools, right? So I'm looking at it as just another type of false positive. Granted, we don't want those, but if that's what it is, then I'll accept that. So if this can get me, if this can take something as abstract as threat modeling and kind of gets me to this very quickly, I don't mind investing a little bit of time to say, you know what, it gave me 20 threats and I dismissed 5 because they were absolute rubbish. But the other 15 had some merit. You know, it's not going to take me a lot of time. It would take me a lot more if I were to start from scratch by first going over the Kubernetes documentation, going over my notes, decomposing all of it, and then starting to research again manually, hey, what are the threats against this and that? And this thing very quickly is going to give me this stuff. So I have a basis of further research, basically. Just zooming through those really quickly, and then down to the storage components. Those are the ones that it had decomposed. A lot of stuff there. Okay, so just a quick recap of what we did. We defined CCCS to GPT-4 or the LLM. Then we asked it to decompose the target system based on CCCS. So we have this predictable outcome of sorts. Because if I just tell it decompose it, I don't know what it will do. So, but at least in this case, I'm expecting it to decompose it into those 4 layers. And when it doesn't, I can just say, hey, you messed up here. And it usually apologizes and does it. So, and then finally, I instructed it to carry out a threat model based on the decomposition results in the previous stage. So some closing thoughts for me with regards to this. So on the positive side, I think it's relatively easy to get started with this. You know, I didn't build a custom model. I didn't do any training. The only thing I did was think of CCCS independently of AI or anything. And then I just wrote some English. I'm not going to call it prompt engineering or anything fancy. It was just me knowing what I want and then articulating in English and then reading what it's writing and then asking it to make changes. And then the output, here's what I like too. The output can be tailored based on your audiences. So typically, especially at large companies, you do have different teams specialized in different areas of the infrastructure. And what you can absolutely do, for example, after it generates the threat model, you can tell it, hey, I want you to rewrite the threats for the storage layer in a way that would make sense, or you know, that is destined to the storage team or someone handling those systems. And it will do a decent job with that. So again, very trivially, I can just ask it to do that type of work, and then I will just have to review it. And then you can also, like I said, you know, the strike categories and ASF, those just part of the template that I defined. I'm like, I want you to include these things into the response. You know, done. So you can add other things into it. Like for example, you might say, I want the threats numbered in a certain way. I want you to group them as like, all of these things usually take time if you're going to do them manually, but you basically build it into the template you need and it's done. And like I said, I think that this gets you fairly quickly to a template that you can then use as a foundation to do the rest of the work. Updating is very easy. Who hasn't had their threat model invalidated after they've polished it because someone then pushed a change later? Right? I mean, that's a fact. And that's why I think having threat models up on a wall is just, you know, you take all this time, you polish it, you think you have all the flows and whatnot, and then, you know, it's just a fact. Change is going to be continuous, and how do you react to this quickly? It's super easy for me, after decomposing the system and having it threat modeled, to then say, oh, we just added a new S3 bucket, or we just added, you know, such and such thing. You know, recompute this thing. What are the implications to the threat model you built? I don't have to do anything in that case, in theory. And like I said, I've talked about why this is a learning tool. I think because it's imperfect and you expect it to make mistakes, just like if you're overlooking a colleague's work or you're explaining something new to someone, it forces you to re-examine your understanding at a depth that is greater than what you had before. On the downside, you need to verify the output. So LLMs make stuff up, and you can mitigate it with something like based on how you constrain the analysis, but you still need to verify what it's doing. In some cases, it's more nuanced than others. So sometimes you read something, it looks good, then you do a double take and say, oh no, that's actually not right. What's even more frustrating is it's very easy to trip an LLM. Like for certain things, if you go back and ask it to correct itself, and it corrects itself, and then I sometimes just want to mess with it, and then I try to argue the first point just to see what it says, and it gets into this type of loop. If you've tried to use it for code generation or writing unit tests, it's just sometimes absolutely hopeless. It'll just get into an endless loop, and it just produces more and more garbage, and it digs an even bigger hole for itself. It does take a few iterations, so this output that I showed, in my opinion, is ideal. I could just take that and show it to an engineer. That's not the initial outcomes I was having, so it takes time to get to that. And yeah, so I did mention I'm working on something that allows you to just get this output with little effort on your part. I don't think everyone's interested in, you know, defining triple CS. Like people just want to say, hey, this is the thing I'm trying to analyze for threats. Tell me what you have, and that's what I'm trying to simplify. Yeah, and the quality of the analysis can be inconsistent. So one example is, you know, even in the previous slides, and sorry, I had to go through them quickly, but some of the threats are great. Like you look at it, it's very specific, it's talking about this component, and it's giving you a real scenario. And in others, it'll say, well, there's a threat of, I don't know, a breach, and the reason is, well, if this component is misconfigured, then it's going to be vulnerable. Well, yes, I knew that, but okay. So sometimes I'll go back and literally say, you know, this is meaningless. It's trivial. Yes, you're pointing out the obvious, and so this is the kind of stuff that needs to be ironed out. So yeah, that's kind of what I had. Triple CS is part of something that I want to make available. I have something called the Open SDL, which is an open security development lifecycle. I think we're in the business these days of securing products and services. I know we still talk a lot about is it AppSec or is it ProdSec, or I think none of this matters. Ultimately, these days, it's all about securing a running product or service. And if you neglect the infrastructure side or the software side or how you deploy something or how you operate it, it's going to end up leaving your service vulnerable. So that's the Open SDL is my effort to hopefully have an open source way for a secure development lifecycle. largely using open source. And the CCCS framework is just part of that. And if you definitely reach out if you're interested in AI-based threat modeling, if you want to play around with what I did there. And yeah, that's all I had.
Thank you. And then I invite all of you to stay for the keynote, for the closing. Okay. Questions? Anyone? Ladies first.
Thank you for your presentation. Can you be a little bit more specific on what are the inputs for the threat modeling part? What do you have to tell ChatGPT?
Yes. So, as I mentioned, I did say there was a little bit of hand waving where I said, oh, CCCS, and then give me the threats. And so, I mentioned how in the course I was teaching students that for every one of the CCCS layers, there's certain security primitives that we want to see. So for the control layer, for example, we mentioned how you want to have solid IAM, how you need to have logging, and so on and so forth. So for each one of those layers, I actually defined to the LLM what I need to see. And so while it's going on through the decomposition, it's trying to look for these things and highlight them to you. So it might say, one threat is at the control layer, insufficient logging might be this or that. And that's the job then of the security engineer to go back and say, do we have sufficient logging there? That's kind of my thinking, yeah. So for some of those threats, yes, it might be theoretical, but again, I don't mind that, because if this is a new system I've never looked at before, and I'm trying to make sure that we're setting things up in a good state, I'm going to go and ask those questions to start with. And if engineering does confirm that such and such control exists or not, then I think I've moved forward there, because then I can absolutely raise a ticket and say, oh yeah, we're supposed to be doing this here, I have confirmation that we're not, hence we have a defect now.
So for the threat modeling part, do you need to provide a knowledge base, for example, PCAC or CWE?
In this case here, I didn't provide anything. I just specified the controls I would like to see for every layer, and I'm kind of seeing what the LLM can come up with. Yeah, good question though. The other thing I want to explore is custom models. So I'm pretty sure it can do a lot better with custom models geared towards threat modeling, preloaded with some of the things that you mentioned. Yeah.
First of all, great talk. Thanks so much. I think I have a couple of questions. So the first is about the decomposition.
Yeah.
And I just wanted to know if you compared the output that you're getting if you don't do decomposition at all and just threat model Kubernetes or whatever, versus doing the decomposition first and doing it. And second of all, have you tested this with maybe less known products, let's say building a small service, like a file sharing service in Django or whatever, so does it work well with less known stuff?
So for the first part, yes, the answer is yes, and that's why I was personally sold on priming it with CCCS first. It's not that it wouldn't do anything, but as a security engineer, I like things to be predictable, I like that repeatability, and I'm also trying to mitigate the unknown unknowns problem. And the fact that I predefined these 4 layers before anything, I wanted to kind of try to fit everything in there, and I think that it would reduce the chance that something might be missed. So yes, I did. Yes, you can ask it straight away without any guidance, but I want repeatability. I don't want the same question to be answered in 10 different ways. That's not really for. It might be good for writing marketing copy, but I think for security you want something somewhat consistent. As for the second part,
so less known applications or a custom.
Yes. So in that course, okay. In the course, we have a hypothetical threat modeling scenario where I came up with a live production environment that is hosted in AWS. And so I had a write-up for it for the students. Now, the students were not using LLM. It was, for them, they had to manually do the threat modeling. But I took that description and I fed it to GPT-4, and actually it did fairly well. There were, all of the downsides that I mentioned earlier were there. There were some things that were inaccurate. It missed some stuff, so I would go back and say, hey, you didn't mention anything about, such and such component, and then, it would go back and say, oh yes, okay, I overlooked that and whatever. So, so it did reasonably okay, but the less documentation there is, so for example, like I said, I would point it to other, even known things, and it would just come up with very trite stuff. It's just like very canned things. And I would challenge it, so to speak, by saying, hey, look, this is nonsense, it's very superficial, I need you to get technical. Other things I would have to say sometimes is, make sure for every threat you're mentioning, it belongs to an actual component, and I don't want it to be generic, I want it to be specific, and so on and so forth. And so, yeah, that's the kind of back and forth that I find myself having to do. That's why I don't think that if this is going to be a useful tool, I don't think people are going to be that patient to play around with it. Something needs to kind of make it accessible. That's what I'm trying to get to. Yeah.
Awesome. Thank you very much. Great presentation.
Thank you. Appreciate it.